So in this part, we will see how do we evaluate the cost of integrated circuits. Now, integrated circuits are fast becoming a significant cost. This is especially true if you look at commodity components like disk or flash memory, DRAMs, or even SoC, system on a chip, right? So you have all the components to make the integrated circuit work. So here is a very standard equation that the integrated circuit cost is nothing but the die cost plus the testing cost plus packaging cost divided by the final test yield. Now this is important to remember that when we look at the cost of it, there is a cost to manufacture, there's a cost to test it, there's a cost to package all of it, but then the test yield is the percentage of good dies that you finally, that survive all these testing procedures. So it's important for us to analyze it. Now, most often, many of the costs are fixed in this, and it has nothing much to do with computer architecture. But one thing that we control a lot is the die area and the amount of components that we want to put on the die, right? So as architects, we build, multipliers and adders, and we want more memory. All of that directly translates into requiring more die area, which translates into increasing the die cost. And that's why we are looking at all of this. Okay. So now, if you want to see what is the cost of the die, the cost of the die is nothing but the wafer cost divided by the dies per wafer into the die yield. So the standard manufacturing process that is even continued into today is you build a wafer, right? Wafer has several dies and you chop them into smaller dies, and each die is then individually tested, then packaged, and then shipped to consumers. Now, the standard way of looking at this figure is something like this. So if you see the two view graphs here on the left, you have one which has a wafer. So you can consider this to be a wafer. And then this is the actual wafer design that you get. And the ones in the center are the working dies, right? Because all these ones that is there, you cannot use them. Wafers are again circular in dimension as opposed to square. So this is how the design is. So you design the wafers to be square, but because of the lithographic process, they are circular in nature. So some of these at the corner, they get wasted. And the only ones in the center are the working dies. So here are two examples. On the left, what you see is dies with certain area, right? This area is greater than the ones on the right side. These have lesser area, right? So you can clearly see that in this, we can, for the same wafer size, right, the diameter, we can have 4 dies, whereas here we can have 9 dies. So the wafer size and the die area, the overall die area, has a tremendous impact on the number of dies that you can get per wafer. Okay. So now that we know what is the die cost, which is the wafer cost divided by the number of dies per wafer multiplied by the die yield, now we can say what is the die cost, right? We can further go into developing some equation for the total number of dies per wafer. Okay, so when it comes to this, here is the actual equation, which is the dies per wafer is nothing but pi into wafer diameter by 2 the whole square divided by the die area minus pi into wafer diameter divided by square root of 2 into 2 into die area. Now, the first term is the ratio of the wafer area to the die area. Obviously, we're looking at the total wafer area to the die area. And the second term compensates for the square peg in the round hole problem. That is, if you go back, if you see here, you see that this is a circular die, right? This is a die, and all these ones, this one, this one, this one, this one, this one, all of these are wasted, right? So the second term is actually doing compensation for that. So what you're doing here is you're dividing the circumference, which is pi into d, by the diagonal of a square die, and it is approximately the number of dies along that edge, because those dies are not any more useful for your product, right? So here is an example for you guys to try. This is trying to find the number of dies per 20 centimeter wafer diameter for a die that is 1.5 centimeter on the side. So you can try to solve this problem. It's a straight substitution problem. You want to make sure when you solve this problem that all your units are in the same metric. For example, if you're looking centimeters, use centimeters. If you're trying to do millimeters, to make sure that they are in millimeters. That way your solution will be accurate. So here is the solution for the problem. So the number of dies per wafer will be nothing but pi into 20 by 2 the whole square divided by 2.25 minus pi into 20 divided by square root of 2 into 2.25. So you subtract those number of dies along the edge, you get around 110 dies per wafer. So if you have a fixed wafer cost and you're interested to figure out what are the number of dies per wafer, then that would be around 110 for this design. Okay, so we're looking at a number of dies per wafer for a 20 centimeter wafer diameter, and each die is 1.5 centimeters. So the number of useful dies that you get is around 110. While this answers, some of the issues with the die cost, what it doesn't tell us is, it doesn't tell us what is the die yield. That is, what is the number of actually good dies or working dies, right? So if you look at this next slide, you will see that while these two graphs was what we showed before, these are the two actual designs that we see with some defects, right? What are these defects? These are generally what we consider as manufacturing defects while the die was being produced. Now keep in mind, today's die are pretty complicated to design, right? These are not like straightforward architecture design where you put some these logic gates and your die is done, right? These are highly complex dies. For example, today's processors, right? So the processors, the logic, then you have the cache and the network. All of this, if you put together, you would probably have anywhere between 8 to 9 layers, metal layers, right? So at the most bottom layer, you would see most of the logic. Layers 1, 2, 3, probably up to 4. These are all the layers for your logic, right? So logic and mostly your caches. So this is your processor, architecture, and so on. So you have 3-4 metal layers just for designing that, okay? Then when you go into the higher layers, right, when you go to the next set of layers, these are called intermediate layers. So the bottom layers are the local layers, the middle layers are the intermediate layers, and the top layers are the global wires or the global layers. The intermediate layers are mostly for networking. I mean, it is used to connect different routers or different crossbars. So they are in the intermediate layer. And the top layer are mostly for power distribution. So you have a power system which drives various components. So they are all at the top layer. So each die will have up to 7 to 9 metal layers, and they will have highly dense components. And all of that is built, right? So you have a lot of etching, a lot of lithography. You will create different wires. Those wires are, to be connected and so on. So you will have some defects. This is given today, given that we are scaling technology to 22 nanometers and going down to 9 nanometers. We are assured to see several defects in our components. And this is not something that is new. I mean, we know this very well. So if you look at what we are designing here, then we will see that the previous calculation, it just uses the maximum number of dies per wafer. But what it does not tell us is the percentage of actually good dies on the wafer. So we need to know way to calculate it. So in the same example that we saw before, on the left side, if you see, because our die was area was larger, we would only have probably one working die in the same defect density, right? This defect density is nothing to do with the processor design. It has to do with the lithography, right? How the process is being built, and the defect density is normally same across different designs. So if you have a die which is going to be, with the area, with a bigger area of the die, then you only have one working die. Whereas if you look at the same design, with good dies, I mean 9 dies that we could create, we'll see that we have 1, 2, 3, 4, 5. So we could probably have 5 working dies here with the same defect density as opposed to the other one. So the die area has a big impact on the actual performance, right? Because the yield is completely depending on how your defect density is spread out, right? So one of the design considerations that people take into effect is how large should my die be. So the larger the die is, the probability of good working dies is fewer, right? Because of the way the defect density works.